Good morning, good afternoon. This is Andrea Copping at Pacific Northwest National Laboratory, and I want to welcome you all here. We are putting this online forum together as part of Annex 4, the initiative under the Ocean Energy System to look at environmental effects of wave and tidal energy development. We have been planning to put these together for some time, and this is really the first we've done. But what we wanted to do is provide an opportunity for the research community, many of whom are dealing with very similar technical problems in different parts of the world, to get together on some and focus on a particular problem. We can't all be traveling all the time and getting together ideally in the same room, but we've got, there's no point in us all solving the same problem in every part of the world. If we can do it jointly, we can be much more efficient. Besides, it's kind of fun. So we're very happy today, very grateful today to Gail Saluski and her group at the University of Maine, who are going to take the lead here in looking at a question that came up really, I think a number of people were talking about at the EMER conference in Scotland not long ago, is how we deal with data coming out of active acoustic instruments around tidal and wave devices. So I'm just going to turn this over to Gail, who has some slides to set the stage. But the point here is really very interactive, discussing the matter. I will tell you this this session is being recorded, so we'll have both slides and audio, and they will be mounted up on Tethys. We'll send you all an email later with the link. And we're really hoping that however we get to today within the hour, that discussion can then continue online. So Gail, thank you so much for your effort in this, and I'm going to turn it over to you.
Okay.
I would like to say that I will ask everybody who is not speaking to please mute your microphones, because then we take away any additional noise. Thank you. Go ahead, Gail.
Noise, what a great introduction. So I'm Gail Zidleski, and I think I've met most of you before. I also have in the room with me Haley Beeman, Garrett Staines, and Haiju Shen, who the three of them are really the people that deal with the data more than I get to, unfortunately. But I thought it would be useful, and it's kind of interesting to see everybody who's on the call who is interested in this topic to just talk about some of the experiences we've had in regard to dealing with active acoustic data. And I think really the topic that came up at the EMER conference was about turbulence, but we kind of stepped back and said, well, we'll talk about noise in general and then turbulence as a subset of that, and then talk about and open up discussion. And so I'm going to go through some slides and just show you some examples, and then thought what we really want to do is come back and have some discussion around that. I'm not quite sure how we'll manage who's talking when, but anyway, so what I thought I'd do is show you the examples, and then we can go back and talk about whatever people want to talk about. Now, my group here, we've talked a lot about, and they've used the EchoView Acoustics Forum quite a bit to kind of post and think about solutions to problems. And so what we thought that this might offer through the Tethys website after this forum would be a way for us to maybe communicate online through comment boxes or whatever. That would be kind of like that acoustics forum that EchoView uses. So if people are familiar with that, that's kind of the idea we were going for. So anyway, I'm going to move to the next slide and just say that first I'm going to go through just noise that we've experienced, how we've dealt with that, and we can come back to that or not, and then move into turbulence and how we've been dealing with that, which we've been dealing with it in kind of a simple way, and then John Horne will talk some about how they've been dealing with the data they've been looking at in Admiralty Inlet. So I'm just going to skip forward here and show you some of the noise that we've dealt with in the past, and it's really, some of it starts off with problems that can be hopefully eliminated in some cases and not in others, or dealt with through processing. So the first thing is system interference. So in the past we've used single beam echo sounders along with a DIDSIN and an ADCP, and you can stick in whatever gear you use that might conflict with various different other gears. And the image on the top right is an image of when you have an ES60 echogram or an ES60 running at a certain pulse duration. The DIDSIN unit actually creates this noise signal. And so the solutions are obviously don't use them together or duty cycle them. But what we did find, at least with the Didson, is we could adjust the pulse duration of the echo sounder to not have that noise anymore. So we were able to kind of work around that for the Didson. The bottom right is an example of an echogram with where the arrow is pointing is an ADCP pinging. So in the past, we've dealt with that in two different ways. One is to just treat the whole section where we know we're collecting ADCP data and pull it out as a bad region. But there's also an algorithm in EchoView which is called intermittent noise removal that we've used in the past as well. So again, this may be simple and everybody may be familiar with all of this, and I just thought we'd throw it out there and we can come back to it to other ways of processing this or discussions about how to deal with these kinds of things later. In terms of other system interference, many of you have probably dealt with this electrical noise or noise in the environment that is difficult to isolate. If you can isolate it and eliminate it, great. Sometimes that involves using only DC power to power your units, and some of you are using only DC power anyway. We have interference from boat electricity or the power on the boat and other things that we deal with. Sometimes applying a threshold works to pull out the noise, and sometimes we remove whole sets of data from the data sets. And again, we can come back to this. These are just some examples of what some of the electrical noise has looked like in some of the data we've collected. Random noise, and so the other thing that happens is boats go by with a similar or even other frequencies that are not what you're recording, and this is what a boat echo sounder looks like as it moves by, at least when we're sitting there. And what I'm showing here is just, we usually treat that as a bad data region, and I bring this up simply because the metric that we use to look at presence of fish anyway is total backscatter in the water column. So we don't typically just take out a section of the data, we will take out the entire data set, that set of the data out of the data region altogether. So again, that's just another example, but obviously more manual processing because you don't know when a boat is going to be going by when you're actually going to be collecting data, especially over a long period of time. One final thing about other noise, these are actually data from a side-looking site that we've used, and in this case we're using single target detection. But one of the things that you can see in this slide is where it indicates a rope, which is not fish, which interferes and is in the view or within the echo sounder view for one tide and not another tide. So you can obviously manually exclude this as a bad region, but what you can see, since it's a rope, it actually changes distance. So you can't just take out a certain distance or a certain depth range, or actually this is a horizontal range in the echogram. One of the things that we've been doing, Haley's been developing a model to actually remove that noise from the data set and apply it to a long-term data set. Okay, now getting into turbulence. So as we've all been probably dealing with turbulence or entrained air at the surface, the diagram on the left kind of shows entrained air at the surface in some of our echograms. And then on the right, what you see, and what is most disturbing to us, is the fact that we remove the top 10 meters of the water column because that's where we mostly see turbulence at the surface, yet we're missing these great schools of fish in those regions, which maybe is just something we need to deal with, but if we can find a better way to deal with turbulence, perhaps we wouldn't have to eliminate those data. Moving on, that entrained air obviously can go further than 10 meters into the water column, and the diagram shown on the left shows that. You can see the green line is actually the 10 meters that we usually eliminate from our data analysis. On the right, there's actually an image from a Didson, and it is definitely turbulence. So sometimes we have both of these units there, and we can verify whether it's turbulence or other sources of an actual signal. So possible processing and analysis solutions. One of the things that we've done is actually moved away from stormy periods. So we tried at the beginning when we were doing our work to stick it through any storm that we were trying to collect data in, and sometimes all of our data ended up being big turbulent streaks like this. Now, some of you are stuck with this because you're bottom mounting over a long period of time. So obviously this needs to be thought about a little bit more. In our case, we deal with this by taking out a bad data region. Again, this example is for when we're using total backscatter as an indication of fish presence. So we take out those bad regions by hand. There are other automated techniques, resampling or using school detection, which John will give an example about in a little bit. But a lot of that still needs manual ground truthing. So obviously there are various different solutions. And also we can come back to this if you want. So that's kind of my noise issues in a nutshell. And I'm going to turn this over to John to let him talk about some of the work they've been doing in Admiralty Inlet, which is somewhat parallel, and then we can come back to whatever issues people would like to discuss.
Okay, thanks, Gail. Good morning and good afternoon to everyone. If we advance to the next slide, which is number 10 by my count. Run into this as a general challenge to all of our acoustic data, not just with the renewable applications. So this is drawn from a number of different approaches, and we found that this is actually quite a universal and apply to non-uniform noise and or turbulence. Gail has summarized, there's roughly 5 ways that we've thought about this, and I'll really focus on the last one at the end. You can effectively ignore it with a depth exclusion, as Gail's already illustrated. You could potentially stretch out noise depending on what your signal is that you're interested in, because anything that's not signal is noise, but typically that will bite into what you would consider data, and we've got to make that trade-off reasonable. If you're interested in single targets or target tracks, then you potentially could look at thresholding, but depending on your signal-to-noise ratio, that may or may not work for you. We've tried a number of the differencing to try and isolate essentially the acoustic characteristics of the bubbles, all its different permutations and combinations, and really haven't quite come up with a generic or successful approach. So we've kind of put that one aside despite a fair amount of effort. What we have found to be fairly robust is using a fairly specific set of school detection parameters for the shapes, what came from the shapes module with view, and I'll illustrate how that's applied. Initial effort for this was done in a marine renewable setting. We were trying to characterize the water column fish and macrozooplankton in the presence of strong turbulence, and for us it wasn't necessarily just storms. Tidal states coming through the passage where we were sitting certainly had a variable amount of turbulence as it went through. But then we've taken that and used it at other sites in a temperate fjord up here where we're having a project looking at hypoxia, looking at fish and zooplankton distributions. That's kind of an example of mild turbulence, which I can show. And then finally, predator-prey interactions between seabirds and fish, and that presented a whole range of noisy environments from mild through turbulent, strongly turbulent. So if you go to the next slide, number 11, I'm going to show 3 different examples of using the schools detection module within EchoView, and just give you a sense of the processing, what the raw data looks like, and where we end up. All these examples are using 120 kilohertz data. That's not chosen for any particular reason. This is the Admiralty Inlet bottom deployed echo sounder, so this is what we had available to us. We do our routine for passive noise removal prior to the turbulence detection, and we do impose on this set a minus 75 dB threshold. That particular number does play a role in impacting how your pixels or voxels are grouped in the schools detection, so that that is always our starting point for this routine. You have your surface exclusion line, and that's really to get you into the far field and exclude the ring down, and Gail already showed where that may or may not hurt you for where your data interest region is. And after that, then we can actually apply the school detection parameters, which you'll see as black outlines, applied below the surface exclusion. So that may or may not help you if you've got near surface or near boundary objects or beasts of interest. After running the parameters, then we can apply those school detections as a bitmap mask back onto the original data to exclude the turbulence. So if we start with the examples on the left-hand side of this slide, you can see that the bottom, or the surface exclusion line first is the bright green line, if you're not familiar with EchoView. The feature, the turbulence feature, extends from the surface right through to the bottom through the whole water column, and you've got a strong signature coming up or down a slope, depending on which way you want to look at it, and a second bottom to give you a summary of the echogram. The next slide, if you were to click forward, and it may be hard to see depending on your screen and the size of your image, has applied the school detection to this feature, and it's actually the black outline around the periphery of the feature. This very strong scattering stays in the middle, and the background itself has been changed to white just so it's a heavier contrast. If you advance your slides again, beside that image just shows what becomes the bitmap mask that would be overlaid on the raw data, outlining the turbulent feature, and notice that it's not being excluded above the surface exclusion line. So everything below that, and you can play with your lines to get pieces in or out near your surface boundaries. The next example on the right side of the panel, kind of a medium set of turbulence extending through roughly half the water column, similar depth to that on the right-hand side, which is about 55 meters at its deepest point here. It extends from the surface into the water column, variable intensity, variable shapes. If you click forward, then you would get the school's detection parameters. You can see the background black. And advancing again, you've got what is used as the bitmap mask for what we call the medium turbulence and extending through parts of the water column. So the next question you might ask, well, that's fairly straightforward and a fairly uniform example for strong through the water column and medium through parts of the water column. What happens if you get a set of mixed conditions in the same data frame? So if we advance the slide again to what is officially numbered number 12, here's an example with mixed conditions, and this was in a mobile survey going over the lip of a sill, where on the left side of the sill you can see kind of a partial or medium intensity turbulent feature about halfway through the water column. More to the middle of the echogram, a stronger one extending right down, intersecting with the bottom. And then to the right, a amorphous cloud of individual targets so that you can see other scatters in the water column. If you click through, there's our school's detection, and it's putting groups together to the left of the sill, on top of the sill, but not including those scattered targets, which you wouldn't want because that's the beast that you're trying to insonify or aggregate and count. And finally, if you click through to the last part, shows you the bitmap mask taking out those the dispersed targets. This is not a perfect method. If you go to the next slide, number 13, just thinking through some points I'd like to make about constraints with this. First, we do use a minus 75 dB threshold over the whole raw echogram. We found that if it was a lower threshold than that, it really kind of messes up your contiguous pixel selection in the turbulent features that you're trying to extract. And how did we get there? It was really a trial and inspection given a place that we were comfortable with, what we know what was biology and what were bubbles. There is a frequency dependence of your turbulence, meaning bubble sizes differ. This in part will impact the frequency that you may choose to use to analyze your data. And that's illustrated below the text on the left-hand side, where this is my crude drawing, where you have a more intense portion of the aggregation surrounded by less intense. And depending on your threshold and depending on your choice of frequency, that's going to determine that size of that feature, a turbulent feature that you want to pull out. It also illustrates why the frequency differencing approach really doesn't work. If you've got a variety of bubble sizes and therefore different resonance peaks, you're not going to get a uniform selection of a feature. So you can play with it a little bit between the threshold and your school detection parameters, but we found that it just isn't as effective. So it's just a point to remember if you've got the choice in looking at which frequency to use. The third point Gail has already made, that you may indeed have fish or zooplankton aggregations intersecting with your surface itself, or where you've arbitrarily chosen that surface exclusion line. So something to be aware of, and you can be clever about where you put your lines and how you put your logical analytic regions, but it's a constraint for bulk processing. And another point is that in these highly strong flow dynamic regions, we found that some of these turbulence plumes that get evected down into the water column also get pushed around by the water a little bit, so that you could have a deeper turbulent feature that actually doesn't intersect with the surface. And actually, I didn't make the point earlier and should have. It was a combination of the aggregation detection plus an intersection with that surface exclusion line, which is what we used to distinguish shallow biology with turbulent features as our arbitrary rules as we went through our large data set. So it was a combination, and I should have pointed that out earlier. In the example here in the lower right of this pane, you've got a turbulent feature that's swung to the right, and if you are moving into the screen, you can see that you would detect what would be considered strong backscatter at depth, and it may or may not be connected to an entrained bubble plume that's coming down from the surface. Those are the sets of the examples that we've had. They've all come from Admiralty Inlet, which is the proposed Snowpud open hydro turbine site. But again, we have applied that to this exact same processing to other spots. So with that, I'll turn it back over to Gail, and we can go to the discussion on the next slide.
Okay, so I guess, again, I'm not quite sure how this will work, because if everybody starts talking at the same time, it could get complicated. But, and I don't know if Andrea or Luke would have an idea of how to do this, but I thought I would just, this is the very same slide I started the presentation off with. And I thought maybe the first thing, is there a topic that we didn't cover that somebody might want to suggest that is important that we missed?
This is Andrea. I suggest that people just, try to sort of jump in and introduce yourself. Let's see if we can keep it from becoming a circus, and let's just go for it. It's Andrea. I'm thinking that while people are still sort of digesting what areas they're particularly interested in talking about, why don't maybe, Gail, you just want to go through these various areas and see if people have some thoughts. I also want to provide a little time. Beth Scott and Benjamin Williamson out of Scotland, I know, have been dealing with this issue for a while. I don't know if there's any particular things, Beth or Benjamin, you'd like to sort of add to what's been said here. I know you don't have any slides up, although we could certainly put some up if you sent them to us. But you guys, I know, are very much in the middle of this too. but you do need to unmute your microphone if you want to talk.
Okay, hi Andrea, can you hear me?
Yes, go ahead, Benjamin.
I don't know whether Beth would like to go first, but anyway, I'm Benjamin Williamson from the University of Aberdeen in Scotland with Sean Fraser here as well. And I think that was a great presentation from Gail and from John. And just to echo really that we're having a lot of the same issues here, some of which were solved in similar ways, but for us at least, it's far from a completely solved problem. For us, having the platform on the seabed certainly helps in that we isolate our sensors to some extent from the surface entrained bubbles. Having our sensors further away from the turbine as well also isolates us from to some extent from the wake effect of the turbine. So electrical noise, yes, we'll solve that by DC power supplies and some quite careful filtering, but an important consideration. The system interference, basically multiple conflicting acoustic frequencies or possibly lower frequency components than the fundamental. Gail's slides on trying to remove this is a great approach and one way of going for it. The way that we've set it up is we have a central controller on the whole platform, and that basically schedules all of the different frequencies from pinging. So every ping is placed in time with a sufficient amount of decay time afterwards to allow the echoes to decay back to background noise. So we have a 38, 120, and 200 kilohertz EK60, but we synchronize that with a 260 kilohertz multibeam. So it's just another way of going at it. Rather than having the noise and then trying to remove it afterwards, we attempt to synchronize, and then if there's any periods when the synchronization is lost, then we're trying to employ similar either temporal or spatial masks, as Gail discussed. So yeah, exactly the same kind of problems. Yeah. As for trying to remove the surface entrained bubbles at the top, I think that was great from what John showed. Yes, it certainly does mask targets. If we're looking at seabed-mounted tidal turbines, then potentially for some of the stages of the tide, we've got a clear field of view of the turbine on the seabed. But certainly at the EMEC site in the north of Scotland, we're finding at some stages of the tide, the surface boils are extending all the way down to the seabed. So that's something we're actively working on, and I hope we can continue to discuss in the future. And then perhaps just the last thing to mention, which Beth might like to elaborate on, is that although it certainly isn't a noise, it's an artifact that's masking potentially important biological features, we're also finding that the birds, and so therefore probably the prey as well, are using this turbulence around the site as an important foraging habitat. So at the same tidal energy site at EMEC in Scotland, as well as the seabed platform, we've also carried out surface surveys with James Waggett, another PhD student here, looking at basically the distribution of birds across the site and therefore prey in relation to turbulence, basically, either measured using the ship's echo sounder, a multi-frequency EK60 again, or using quite a complex 3D model of the flows and the turbulence in the site, developed by our colleagues at Plymouth. So really just to echo that we're having the same problems, but it's also an important feature that we're trying to pull out and look at understanding, basically.
Hi there, it's Beth here.
Yeah, go ahead, Beth.
Yeah, Benjamin and Sean are in one location and I'm in another location, having just got off a boat today and decided to work from home because I'm a bit exhausted. Exactly. So Benjamin's put that all there. So I think the thing we're most interested in and are just starting is this categorization of different types of turbulence. And I do agree. I think the school, using school detection to try to categorize the turbulence. I'd love to hear more about that, how successful or unsuccessful that's been. I'm at a disadvantage. For some reason, I can't see the slides, but you guys have done an excellent job of describing them. So, and I've just spent the last 4 days staring at EK60 output. So I feel like I can imagine it. So if you guys, go into some of the characterizations of the turbulence and the pros and cons, that would be great.
John, do you want to describe the masking? I mean, really, we take a lot of it out, so it wouldn't be, it would be how you might characterize it using those techniques.
Just to clarify, what do you mean by characterization, Beth? are you looking to effectively categorize the turbulent features, or are you looking to categorize as descriptors, characterize the features themselves of the features?
Yeah, I mean, I guess possibly a bit of both. Right now, we're just getting to the point where this is what Sean Fraser, who's sitting there with Benjamin, is going to be looking in more detail. And what I see is possibly checking it both ways. That I know we've had Eric Armstrong, the acoustic expert at the Scottish Marine Lab, giving us a lot of advice on this, and yeah, his advice is basically try all different ways you possibly can. The view is so nicely flexible that we possibly come up with new areas. But it's, in my mind, it's a looking at the turbulence as if they were, different. We know that that they're there with the different speeds. That should we characterize it that way, or is it the final fact that what turbulence will become at maximum speeds that we're trying to characterize the different heights of the water column, the different features within it? I'm really not sure how detailed we need to go, but it's such that the masking part becomes that much more sophisticated of taking it out, that you can really start to try to dig in and see those fish we're pretty sure are in there, at least at some abundances.
Okay. Two thoughts. First, as with Gail's approach, we haven't treated turbulence as an entity, and I think that's in part what you're getting to. So I would treat, thinking out loud, kind of have two approaches. One, there are a suite of metrics associated with the school's detection module that could be used to characterize the, let's call them we need a good label here, but the turbulent features themselves, so that you can get areas and volumes and relative heights, and so typical descriptors that you would use just to describe the quantity itself as an entity. Having done that, that may or may not enable you to categorize these. We've used broad categories, what we've today as strong, kind of medium, and weak or mild. And that's really just to break a continuous range of conditions into a small number of easily understood or broad categories. The other thing that I heard in your reply may be a desire to characterize the occurrence of these categories relative to other conditions or other covariates. And in thinking about all the spots where we've run into turbulent water and the differences among them, the bathymetry would need to be characterized. The tidal state would need to be characterized. Gail talked about storms, so potentially wind events to entrain more bubbles. So without having done the exercise, I see the potential, and I guess I would kind of use those three steps to identify the features, derive a set of quantitative descriptors or metrics of the features themselves so they could be compared and contrasted, and look to other covariates so that you could, I don't know if you'd ever get to a predictive state, but at least look at what influences some sort of a response variable that may be a character of the metric of the turbulent feature, or the numbers of features, or the density of features, however you want to characterize a response variable.
So I also heard, Beth, you say maybe that once you've characterized the turbulence, that you'd like to see what other animals or what's within that turbulence, which I'm having a hard time trying to envision because it does get taken out as noise. So I'm wondering if either of you have ideas of how do you pull a signal necessarily out of that?
Well, what we're hoping to use, I would say, is the presence of the bird foraging, that we're pretty sure when they're doing their dives that there is something present. I know my hopes of actually finding the fish there is not, but exactly what John's just said so much better than I did, exactly that once we have those either covariates or identified the features, then we can possibly correlate that with the bird presence and say that that equates to fish presence.
Okay.
Gail, I think that the constraint of this whole exercise, and it would be cool, and especially around the edges of these features might be more biologically interesting, is really going to depend on the signal-to-noise ratio. My general experience, regardless of the source of noise, that's always going to be a limiting factor. So it depends on the acoustic size of your beast of interest relative to everything else that's the noise. And unless you've got a really strong scatterer, whether it be a single organism or a group of organisms, I think it's going to be quite a challenge to extract that out of a turbulent feature, unless it's so overwhelming. And maybe if you get a profile of a seabird diving through all or a portion of a feature, that might be fun to play with just as an exercise to see what you can discriminate the signal to noise. But I wouldn't put that really high probability of success in a consistent way.
Right. So Beth, you're suggesting you'd use other methods to just say birds were there?
Well, we right now we have the data that allows from the shore to tell us exactly when birds were diving. So we're not relying on the acoustic data for that. And basically, I'd be really, really happy if we could just get to the point where we could say, birds are diving and it's this type of turbulence, where they're probably able to catch fish in this type of turbulence. And the other features that predict this type of turbulence is, say, speed of tide and topography. And hopefully take that to other areas and basically say, this is where we expect foraging to occur, so that we can create maps of areas possibly where before people put a lot of money into putting their turbines in the water, we can say which spots are really good for foraging and which spots are possibly less good for foraging. And added to that, now working very closely with a lot of these companies, is actually then the opposite of finding them areas where there isn't much foraging. There's possibly more land, relatively speaking, of course, flow, and possibly better spots for turbines on this very fine scale of hundreds of meters.
Bev, I'm curious, or Beth, I'm curious, how has the avoidance of biological hotspots, to use a label, ever come up as an issue that overrides some of the other turbine placement, either from the developer side or the regulatory side?
Well, just today, actually, we got this is not tidal turbines, but wind turbines. We got the announcement that we're going to put an MPA in exactly the same location we're going to put wind turbines. And no one yet knows how we're going to exactly what they call co-develop these areas. So it's come to a head here very quick because, we have a lot less space than you guys. It is going to come to a head that this idea of very high foraging areas for especially mobile animals may be reasons to move things or change designs of arrays. It's not there yet, but it's certainly coming now that we're getting to bigger arrays with our wind farms.
Okay, well that was I think that was a good discussion. And are there other items that people want to go back to, or there's quite a few of you on here that may have other things to discuss.
This is Daniel Dan from PNL.
Mm-hmm.
Yeah, we just touching on your electrical noise. We have the same experience. We do a fair amount of work, measuring noise in the forebay of a dam and also in the tail race. And of course, a lot of sensors is combination of actives, acoustic and passive acoustics. but it seems they share similar issues as is on the electrical noise part and some of the air bubble entrainment due to turbulence. What we found out is DC power is always your best friend. Then, because it's really hard to isolate the issue and eliminate those electrical noise in a boat. And also those bubble entrainment can affect not only the acoustic echogram and also on a lot of our passive acoustic detections and also the time of arrival estimates, which is required to do the localization of fish and other animals. That's all I have to offer for now.
No, it's a good point. I think that, some of our work when we're doing work from a boat in particular, somebody plugs in a cell phone in an electrical socket and it throws everything off. And so, just being aware of all of those items is really important. And I mean, it comes from a kind of a naive perspective, I guess, but it's amazing that the sources of noise that creep into the data sets.
Yes, cell phone and also even the walkie-talkie.
Yeah.
I can regale you with lots of stories of amazing things, including electric toilets that will give you a lot of problems, and sometimes are hard to track down because they're intermittent. One thing that Gail didn't mention, and you guys haven't mentioned yet, that I'd highly recommend, not only is DC your friend, but even if you're using AC, make sure you ground your units, your transceiver units for the echo sounders. You'll find that you'll pick up 6 to 10 dB right off the top in passive noise, and that may make a huge difference in your processing. So not only potentially look to DC, but make sure that you've got a really good ground for your system, which includes all of the components that are supplying power to your transceivers.
Okay, John, just on that topic, what would be the best way you would recommend for grounding?
Especially on a boat, yeah.
Okay. It turns out that boats can have more than one ground, and there is no silver bullet. You can start with getting as close to or directly connected to the hull as possible, but the configuration of where you're setting up your equipment and what's exposed may or may not limit your access. Don't be afraid to run a wire any sort of distance to get to a better ground. Try more than one. You may even go to ground to the electrical system, an outlet if you can get some metal, excuse me, because that will be tied into one of the ship's ground. And if that fails, I haven't had to resort to this, but you could run a wire over the edge and ground to the seawater.
John, we have done that actually in the tail race. Of course, it's much more friendly environment than your ocean over there. Yeah, we try ground to the boat, to the front, to the end. Sometimes works, sometimes not. So we did try the approach ground all the way to the bottom, and that worked much better, at least for a few occasions.
It's all part of the setup, and I guess I always explicitly build in, especially if you're going boat to boat or site to site, that don't make sure that you've got adequate time for setup and testing, because it often will impact the quality of your data, and you'll pay for it in the lab and curse yourself forever after. And all I'm trying to do is benefit you from my mistakes.
Yeah. And I guess the big thing, thinking about one of the topics down the line would be, what are the metrics people are using? But I brought it up several times that we use backscatter a lot. And if you have electrical interference or noise in your data, that really messes things up a lot back in the lab, like John said. Does anybody have other ideas for dealing with turbulence, or ideas for, Beth's question about characterizing it? I like the idea of thinking about, temporal and spatial relationships with different covariates. But does anybody have any other thoughts on other ways to think about that?
Or does anybody have any thoughts about, I'm not even sure if this is possible, with different frequencies, pulse durations, or ping rates, about trying to improve that signal-to-noise ratio within that bubble layer? I'm not sure if there is a high enough frequency or a low enough frequency or any of that to possibly improve that. Does anyone have thoughts on that?
This is John, and I can offer a couple of thoughts if no one else has suggestions. Okay. It's difficult
Excuse
to
me,
measure.
John, one sec. Mark, was that you asking the question?
No, that was
Sorry,
Garrett.
that was Garrett in Gail's
Oh,
lab.
Garrett. Oh, okay. Thank you so much. If you don't mind saying your name, we're just trying to make sure we...
Right, sorry.
Go ahead, John. Sorry.
Okay. First thought I would have is, and essentially impossible to measure, but you can see it as a response on your echo sounder to look at the resonance frequencies of the bubbles that you've got. If you're fortunate enough to have a suite of frequencies, typically from mobile applications at the surface, that may direct you to using one frequency data stream relative to the others, just because you're avoiding the resonance peaks from the bubbles, which will really reduce your signal-to-noise ratio off the top. That's probably, in my mind, the biggest feature, and you may or may not have the luxury of choice there. Secondly, thinking about resolution, I still think about these turbulent features as entities, so I'm not really trying to look at the characters of them, but Beth, you've really got me intrigued about this now, and I'm going to use this as an exercise. Short pulse durations will increase the resolution of your data, as well as lower the total energy that you're putting into the water for any single pulse. So that is also going to maximize your signal-to-noise ratio around these features, only because that you won't be getting the return as much from a longer duration pulse. One element that you didn't mention that we haven't played with explicitly, but comes into play just with general data collection, would be your source level. So the overall amount of power that you're putting into your transceiver, your transducer, is also going to impact your signal-to-noise ratio. Again, I can't point you to any explicit studies or cookbook type, because this is really lumped into the general turbulent features, are lumped into the general noise category, and I think that the MHK community is really one of the first, or say traditional energy, I'm thinking, Daniel, the raceways or the traditional hydropower applications, is bringing up these features as either a feature of interest or a really dominant noise source, and that typically isn't seen out in our general acoustic applications.
Mm-hmm.
Yeah, this is Tom Carlson. I was wondering if anyone has looked at different beam widths. The idea being to, reduce the ratio of the scatter of interest to the bubbles in a turbulent feature.
We do have to. So. We haven't. Although Ben and Beth, do you guys use different beam widths? Although you mentioned different frequencies, but they're all the same beam width, I'm assuming. And you would need to have the similar frequencies to answer that question, I guess.
Yeah, so the setup that we have at the moment, all three frequencies are 7 degrees. So that's not something we've looked at. It could be something interesting to study, though, and probably a quicker way to look at it would be a surface platform looking down, something like a boat survey through the sites to investigate the different beam widths, if that was something potentially of interest.
Yeah, I mean, we
Yeah, I
do
know
have...
projects that we did in the past at the dams out in the near ocean environment. We looked at a variety of ways of lensing and other things to try to get a reduced side lobes, have narrow beam widths, and then we looked at more complicated multiplexing type applications to get the spatial and temporal coverage that we wanted for a particular survey application. But these approaches get expensive very, very quickly.
Yeah.
This is John. The experience that we've had gets to that just a little bit in that in our surface multi-frequency application, we've had a combined with some 7-degree transducers. We haven't explicitly looked at differences in integration around bubble features, which is one way that I guess you could look to see if the kind of signal to noise in your target versus non-targets of interest have any impact. I don't know if we have a large enough range of beam angles really to provide any insight into that suggestion.
Mm.
Yeah, the work that we've sorry, this is Garrett Staines in Gail's lab. Our single beam work has been with a wide angle, actually a 31 degree, which has a really, really large main lobe and very, very small side lobes. And I'm just kind of thinking anecdotally, that compared to a 7 degree narrow angle that has pretty significant side lobes on the side of its.
We've tried to do comparisons.
We've tried to do SV comparisons, and the issue I ran into with that, you make the assumption maybe right off hand that you're going to get the same SV by sampling the same water, but I think what it came down to was try to picture a school of fish passing by, or even a bubble layer that is large enough to take up the entire beam of the 7 degree. But small enough to not take up the entire beam of the wide angle single beam, and I think that was causing some pretty large discrepancies in backscatter, just I think relative to the amount of empty space within each beam. So I don't know if that helps to clarify, or maybe it makes it worse.
And it might be that we have some data with those two different beams that we could look at.
But going to the ratio of biological signal to, say, bubble signal, just right off the bat, I would think maybe a narrow angle would be the best way to go.
And in our particular case, we were looking at adult salmon, pretty good sized, and beam width did make a difference, but we had to suppress side lobes. And like I said, it's these are sort of non-standard approaches, and you have to do system design work and what have you. So it probably is a stretch, for what most people are currently doing.
Yep. Well, we're closing in on. Let's see, I have 3 minutes before the hour. So there are a few other people on the call. Is there anything else that people want to mention? And then I'll just turn it over to Andrea and Luke to talk about what's next.
This is Mark Bevelheimer at Oak Ridge National Lab. What we're dealing with in the way of noise is not turbulence, so I haven't really said anything, but I just want people to know we're working up DIDSON data that was aimed at an operating turbine, a tidal turbine, And so our challenge is trying to deal with getting the turbine out of the way so we can see the fish. And that's not a big deal, except that the turbine turns its direction every 6 or 8 hours, and it also wobbles when boats go by and when the flows change. So you'll hear more from us in the coming months. And we have a spinning blade that we have to deal with as well.
We know feel your pain. This is Haley in Gail's lab. I would be very interested to hear where you guys go with that. We ended up we manually looked through all of our data for the spinning turbine for that exact reason. So there's definitely some. We need a method to cover that, certainly.
We haven't given in yet. We're still trying.
Good.
Can I ask there, do you have data from, the structure in the water before you had a turning turbine? And if you did, how different is it?
Yeah, we do. We have 2 or 3 weeks worth of data when the turbine was in place. We have data when the turbine's locked in place, so it's not spinning. And then we have another week when the turbine, after the turbine had been removed. So in that sense, we have a pretty good understanding of what the background is, and that's been real helpful. But because the turbine moves, its location spins around like a windmill when the tide changes, that just makes it more challenging. And like I say, it does wobble as well as it comes up to speed, so it's not always in the same place.
I wonder if there's any sort of image processing technique that could take into account more repetitive motions, of different frequencies. I don't know anything about image processing yet, but
yeah, that's a good thought. And again, part of the problem is the turbine turns at a different rate as the tide increases. I think I could be wrong. If it turns at the same speed all the time, same RPM, then that does give us something else to.
Could there be any kind of temporally link something to current speed or time that could, I don't know, that might be able to increase the frequency you're looking for as as time passes and decrease it?
Well, we do have current speed that was collected at the same time, but it's not. If it's a variable speed blade, then there's no way to get it quite accurate based on the relationship with the current speed. But so anyway, I just want to let people know that's going on. I know we're out of town, Gil. We're out of time, so.
That's all right. Thanks, Mark. I guess Andrea or Luke?
Gail, thanks so much. Boy, thank you, everybody. This was a great discussion. And believe me, I speak from a position of ignorance, although that very last point, many of you may know that this is an issue in processing optical output looking at wind turbines. And I know that there are a number of groups that are working on algorithms that can take out that repetitive motion from the optical output. And so I have absolutely no idea if there's an analog to the acoustics of that repetitive blade, but it might be worth something looking at. Anyway, I want to thank everybody for taking the time today. This was a fantastic discussion. It is being recorded. We will have the slides, and it will all go up online on Tethys, and everybody who's on here will get an email when that happens. Particular thanks to Gail, to John, to Beth, to Benjamin, to everybody who contributed here today. And I think we're just going to end this and say thank you, and please look at the material online and continue the commenting online. If it feels like there is a feature or an issue that comes out of this discussion that would benefit from this kind of hour spent online together, again, please let us know, and we're more than happy to set that up.